Okay, Chapter 8 is rational functions and radical functions. Our rational functions are the fractional, like algebraic fractions, so that they have algebraic expressions in both the numerator and denominator. Our radical functions are going to be our square roots, cube roots, fourth roots, and so on. In Lesson 8.2, we'll just be dealing with rational functions and their graphs. The objective is to identify and evaluate rational functions and to graph a rational function and find its domain. First of all, what is a rational function or a rational expression? A rational expression is a quotient of two polynomials. So you'll have a polynomial on the top and a polynomial on the bottom, and you may just have a constant at the top or the bottom, but you could have polynomials, binomials, trinomials, whatever degree. This is a non-example, and the reason it's a non-example is because it has the absolute value. Our rational function is basically a function that has a rational expression. So it is basically a rational expression, but we generally tend to write the f of x equals for our function. Okay? The domain is going to be extremely important in this because with a rational function, we have restrictions, and those restrictions are going to be important. Remember that our fraction cannot have a zero in the denominator. So here's an example, the same example that I used as my example of a rational expression. And if I was dealing with this function, and I should write it as a function here, so f of x equals that, and I was looking for the domain, then I cannot have a zero in that denominator. So in this case, x squared minus 4 cannot be 0. So how do I figure out what values of x will give me 0, or will give me the x squared minus 4 to be 0? I need to factor this, and it's a difference of squares. So I can figure out that x plus 2 cannot be 0, and x minus 2 cannot be 0. So x cannot be negative 2, and x cannot be 2. So those are what x cannot be. Our restrictions is what we call them. So my domain, if I want to write it correctly, would be all reals except 2 and negative 2. Okay, is one way to write it. We can also write it in interval notation. If we wanted to write the interval notation, I would have from negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. So our graphs. Now we're going to look at the graphs of our rational functions. We have something called vertical asymptotes, and this is going to be very important when we're dealing with graphing. It's going to basically give us our general shape of our graph. These are the vertical lines that the graph of a function will not touch or pass through. So you can see I have an example down here, and you can look at the example of that graph. It looks like a graph that we have not dealt with before. But our basic idea of finding our asymptotes is that if x minus a is a factor of the denominator of a rational function, but not a factor of the numerator, then x equals a is a vertical asymptote. So when I look at this, I'm going to have to figure out my factors of the denominator and my factors of the numerator so I can decide if I have any asymptotes. I know that negative 2 and 2, these are my restrictions. Those are what x cannot be. Let's make sure that I don't have one of those factors, x plus 2 or x minus 2 in the numerator. So let's factor this. What multiplies to give me 3 and adds to give me negative 2. And we don't have anything for that one. That one's not factorable. So all we have is the x plus 2, x minus 2 in the denominator. Okay, I'm going to just get rid of this and we'll start over there. So we have in the denominator x plus 2, x minus 2, and our numerator cannot be factored. So I do not have any factors that are in both. So if I look at this, my asymptotes are going to be where x equals negative 2 and x equals 2. The same thing that I came up with for my restrictions up in this part right here. And if you look at my graph here, and I'm just going to to show you, we have these asymptotes, if you can look clearly here. We generally draw these vertical lines, and the asymptotes are going to be where that graph is going either up to infinity or down to infinity, but it never crosses through it. Same thing here, it can go down or it can go up, but it's never going to cross that actual line if I drew this a little more accurate. Okay, now we're going to look at what a hole in the graph will actually look like. So we're looking at, I'm going to take this problem and I'm going to change it a little bit so that the numerator is actually factorable. So instead of having this rational expression, I'm going to have this. All I'm going to do is change that 3 to a minus 8. You'll notice my denominator is still the same, so my domain is still all reals except 2 and negative 2. So I still have the same thing. So when you initially look at this, you think you're going to have asymptotes at 2 and negative 2. But what happens here when I factor this is I'll get x minus 4, x plus 2, and I have x plus 2, x minus 2 in the denominator. So I can actually reduce this rational expression and get x minus 4 over x minus 2. So when I graph this, it's actually going to have a little bit different graph. Okay, so you can see the graph that I got from the graphing calculator, and you'll notice a difference between this graph and the last one. My domain is still the same, 2 and negative 2, but instead of having the two asymptotes, I have this asymptote right here. But the one at negative 2, actually, there's no asymptote there. If the last graph had an asymptote right in here, if you remember, it was right there at the negative 2, and this graph does not. When you actually go into the table, you'll notice that at negative 2 you can't put that in there. It's still going to say error. But technically what we have here, and it's going to be hard to see this, I'll try to do it in blue, but you're going to have an open dot at that negative 2. You can't put negative 2 into this function, the original function, because you'll have a negative, you'll have the denominator be 0. However, you can put it into this function. Okay, but this was my original problem. So when I graph it, I don't have the asymptote, I just have a hole in the graph. You'll also notice when you look at this, because the next thing we want to go over are the horizontal asymptotes. If you notice this graph, the graph gets really close to this line right here, but never actually crosses it. And that's what we call a horizontal asymptote, because it's a horizontal line that the graph is not going to pass through. Now, how do we find horizontal asymptotes? This is a little bit more difficult than just the vertical asymptotes. What we need to do is we have a few rules, and you need to follow these rules. These are good rules to put in your math toolkit because you'll want to remember these. They're a little confusing when you first read them, but then after you do a couple examples, you'll see how it works. Basically, a rational function is sorry, I'm going to move this up a little bit. A rational function is, let me see if I can move this. There we go. Is going to be two polynomials, one over the other. So we have this polynomial and we have this polynomial, one over the other. So in order to figure out our horizontal asymptotes, we're going to look at the degree of the numerator and the degree of the denominator. If those two are actually, the degree of the numerator is less than the degree of the denominator, then my horizontal asymptote is y equals 0. And that's it. You're done. Okay? If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals a over b, where a is the leading coefficient of p and b is going to be the leading coefficient of q. Okay? If the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. There's actually what we call a slant asymptote, which we're not going to go over right at this time. Okay, let's look at the example that I went over in the first problem when we were looking at domain and then the vertical asymptotes. So if I look at this function and I want to find the horizontal asymptotes, you'll notice that my degree of the numerator is 2, and my degree of the denominator is also 2. So my degree of the numerator and denominator are both 2, therefore they're the same. And so my asymptote is going to be y equals, I'm going to have some fraction. The fraction is going to be, I'm going to have to look at the leading coefficient of the numerator and the leading coefficient of the denominator. So in both of those cases, my coefficient's 1, so my horizontal asymptote is going to be y equals 1. Okay, let's just sketch this by hand instead of doing it on the graphing calculator. If you remember, I had 2 vertical asymptotes, one at -2 and one at +2, which means the graph will get close to it but never quite reach it. And then if you remember, now we have the horizontal asymptote at y equals 1. So there's my other line. My graph is going to look something like this. And in this part, this is where it gets a little tricky. You'll have to find some more information, but by looking at my graphing calculator, I see that it's going to go like that. And I have that. This part in the middle could come up a little bit higher. It could be down a little bit lower, and that depends on the actual function and plugging in values. You can look and try to find x-intercepts. You can find some other information to come up with a graph. But since we have the graphing calculator, we're going to use that to help us. Okay, let's look at a couple examples. So we're going to look at this function. We're going to state the domain, find the vertical asymptotes, if there's any holes in the graph, and then the horizontal asymptotes, and then quickly just draw a sketch of this function. So first of all, I'm going to rewrite this with the denominator in order, because I like it in descending order in standard form, so that when I look at it and find the horizontal asymptotes, it'll be easy to see the leading coefficients. Okay. Now, when I need to factor this, I'm going to factor both the numerator and denominator, and then we can look at that. I have x plus 4, x minus 4. So here's f of x equals. And then I have x minus 4, x plus 1. So here's my rational function in factored form. And you'll see that my domain, before I start reducing, I'm going to look at my domain because I need to look at the original function. And I can't have x cannot be 4 and x cannot be -1. So those are possible vertical asymptotes. We need to see if we can reduce and then end up with a hole in the graph. So my domain is going to be all reals except 4 and -1. Okay, now my possible asymptotes are going to be x equals 4. So let's look at our vertical asymptotes. Okay, I could possibly have x equals 4 and x equals -1. But if you'll look at this problem, I have x minus 4 and I have x minus 4 in both the numerator and denominator. So what I'm going to be able to do is actually reduce this. So this is the function that I'm going to be able to look at. And since those reduce, I do have a hole in the graph. At x equals 4. My vertical asymptote then is only going to be the x equals -1. Now how do I find the horizontal asymptotes? So my horizontal asymptote, once you know the formula, is going to be easy, because I look at this and I look at my original one that I have here written in standard form, and I have the degree of my numerator and the degree of my denominator are both 2. So I'm going to take the leading coefficients here and write my vertical or horizontal asymptote as x equals 1 over 1, or y equals 1 over 1, or y equals 1. So I can quickly take this information and come up with a quick sketch of this. It won't be super accurate, but I'm going to use what I have and come up with a sketch. I have a vertical asymptote at -1. I'm going to have a hole in the graph at x equals 4, but I'm going to wait and see what I kind of am dealing with here. I have y equals 1 as a horizontal asymptote. And at this point, I know I'm going to have something either here or here, and something here or here. The only way to really tell exactly is by plugging some values into my function. And at this point, we have the graphing calculator, so we're going to actually use the graphing calculator and come up with a good sketch of this one. And we should come up with something that's going to look like this. Whoops. Now, I need to be careful here because if you remember, I have my hole in the graph at x equals 4. So when I'm graphing this, that's the general shape, and the graphing calculator will make it look like this. But when you actually go into the table, at 4, you are not going to be allowed to put in 4 into this original function, so you're going to actually have error at there. You can't see it on the graphing calculator, but there will be an open dot on that point. Everything getting close to that value of 4 will be really close to that point in either direction, but you can't actually plug in 4 into that function. So that's what my graph is going to look like. The information I'm going to be asking for, obviously, is the domain, the vertical asymptote, the hole in the graph, and the horizontal asymptotes. You need to write that information and then come up with a general sketch of your graph just using your graphing calculator and verify that your work over here is actually correct. Here's another example. This time the function is written in factored form. So when I originally look at this, I can come up with my domain right away. In this case, I have x can't be -2, so my domain is all reals except -2. So I have my domain. If I look at my vertical asymptotes, my possibilities are at x equals -2. And I need to see if that actually is going to be an asymptote or is it going to be a hole in the graph. When you look at the two factors here, I have x plus 2 and x plus 2, so I'm going to be able to reduce this. My function in simplified form is just going to be 3x minus 1. So what ends up happening here is instead of having a vertical asymptote, x equals -2 is going to be where I'm going to have a hole in the graph. How about my horizontal asymptotes? Now this one's going to be a little trickier because I have to look at the degree of the numerator and the denominator, and it's not written in standard form but factored form. So when I look at this, I have 3x minus 1 and x plus 2. When I multiply that out, I'm going to end up with 3x squared as my leading coefficient. I have the rest of it here, but really all I'm worried about is that leading coefficient. And in the denominator, my leading coefficient is going to be x. So when I look at the degree here, here I have a degree of 2, here I have a degree of 1. So my degree of my numerator is greater than the degree of the denominator. So in this case, my asymptote is, I don't have one. So there is no horizontal asymptote because my degree is, this degree in the numerator is 2 and this one's only 1. So my rule says there are no horizontal asymptotes. Now when I look at the graph of this, I don't have any vertical asymptotes. I don't have any horizontal asymptotes. All I've got is a hole in the graph at -2. So when I look on my graphing calculator, I'm going to get this graph that looks like this. It's a straight line because when I graph y equals 3x minus 1, which is basically what I have in the simplified form, I'm going to get a line with a slope of 3 and a y-intercept of -1. And that's what it's going to look like. The only difference is that because of my original problem, I cannot have -2 as a value that I plug in for x. So at -2 on my graph, I'm going to have an open dot. Wherever that graph would have been going through, I'm just going to have an open dot at that point. And you need to make sure you put that open dot there. Like I said earlier, it is not going to be on the graphing calculator. It will be in the table. But everything here gets close to there. You can't put in that number. And then everything here is going to get close to that number. Okay, here's my last example. Here we have 3x minus 1 over 9x squared minus 36. So let's look at the factors. I'm going to put 3x minus 1 in parentheses. And then here I can take out a 9. And so then that factors as x plus 2, x minus 2. Okay, I'm not going to be able to simplify anything here, but let's look at our domain. My domain, because I have the x plus 2, x minus 2, is x cannot be -2 and x cannot be 2. So it's all reals except 2 and -2. Okay, my vertical asymptotes could possibly be the -2, x equals -2 and x equals 2. I'm not going to be able to simplify anything here, so I actually do have both of those. And a hole in a graph we're not going to have because I don't have any factors that are the same. So I don't have any holes in the graph. My horizontal, so here's a different example because my horizontal asymptote in this case is going to be, if you look at our original problem here, we have a degree of 1 and a degree of 2. So my degree of the numerator is going to be less than the degree of the denominator. So in this case, my horizontal asymptote is y equals 0. And that's just my rule, and I need to remember that. Now, when you look on a graphing calculator for this one, and this is where in certain situations the horizontal asymptote is going to work for parts of the graph, but there are going to be parts of the graph where you actually can pass through the horizontal asymptote. It'll never happen on a vertical asymptote, but it does on the horizontal asymptote. So when I draw my vertical asymptotes at -2 and 2, and then I have a horizontal asymptote at y equals 0, you're going to think that it's not going to cross through there. When I look at my graph here, what I'm going to have is something that looks like this, and then it's going to go like this, and it'll look like this. There are no holes in the graph, so basically this is what my graph is going to look like. In this section over here, I use my horizontal asymptote right here. It's never going to pass through that. And here's my vertical asymptote. In this section, the same thing. I use my horizontal asymptote and my vertical asymptote. But in the middle, you'll see I use my vertical asymptotes, but I actually have that point right there that's passing through the horizontal asymptote. And that happens sometimes when we're dealing with the asymptote of y equals 0, and sometimes even when we have a different horizontal asymptote. Like I said earlier, the vertical asymptotes, it'll never cross through because those are not part of the domain. So I cannot put 2 and -2 into this function. Okay, let's summarize what we are doing to graph these rational functions. The first thing that you need to do when you're graphing the rational function is factor, if possible. Okay, we need to find the domain. We need to find the vertical asymptotes. We need to find any holes in the graph. And then we're going to use our rules to find any horizontal asymptotes. And finally, we can use the calculator to graph. Now, some people prefer to they use the calculator to graph. They'll take this and they'll move that up to the front just to get an idea of what they're looking at. And then from that, they can follow these steps. But definitely use your graphing calculator to verify that your work was done for finding the domain, finding the vertical asymptote, finding the holes in the graph, and then finding the horizontal asymptote.